Thank you very much. Okay, where's my little advancer thing here? Okay. Got it. So, as mentioned, I've spent a fair amount of my career working on fuel cells and had the privilege to meet Ken Reef-Snyder quite a while ago, though I work at the low temperature end of his spectrum. However, we're at a stage where the question, what's a fuel cell person to do, is important to us. And so we have to adjust, let's say. So a couple of years ago when I came to Tennessee, I looked into what types of possible applications we could have. Thinking about, just as Ken talked about extensively, the notion of using the fuel cells as an electrochemical reactor. Flow batteries, which I'll talk about through this talk, are one place. We're now starting to work on biomass conversions in this electrochemical reactor construct. And so basically we started looking into flow batteries. What we found was that a lot of work had been done by some people over about 30 years, but very little bedrock existed. And so much of what I'm going to talk about today, especially toward the latter part of the talk, is to build up the foundation for the science here. So let's start with what's a flow battery. Imagine a battery the size of a Home Depot. That's the way I like to talk about it. In general, this is a flow battery. It's a megawatt scale installation. I believe it's in Mississippi, maybe even, or was built there around 2000. Some friends at a company called Electrosynthesis, which was engulfed and devoured and then spit back out by a company called Regenesis, built this system. But you can get an idea of the scale because there's a person down here, if you can see that ant. Ultimately, a flow battery looks a lot like a fuel cell, except for the fact that we're flowing liquids, usually, solutions through the fuel cell type converter. So these are, again, what a fuel cell stack might look like, configured as a flow battery. And one interesting thing that I highlight here, I'll talk more about this in general, but the idea generally is that you have tanks full of redox active agents that flow into opposite sides of each cell of a filter press type stack. The cool thing about this is that you've neatly separated the power conversion technology from the energy side of things. The energy is in the chemicals that are stored in gigantic tanks. So you can scale this pretty much arbitrarily on the energy side just by building a bigger tank. You can scale the power by building more cells. However, the cell converter side tends to be a little bit expensive, and we'll get to that in a minute. So why do you care about having a battery the size of a Home Depot? The answer is renewables on the grid. These show the fluctuation in megawatts of energy coming off of windmills over a daily cycle, and also solar cells over a cycle. Notice that if you look at the units here, these are gigawatt scale fluctuations. The grid doesn't like gigawatt scale fluctuations. I can guarantee you that. In fact, the entire Bonneville power plant in the Pacific Northwest is about a 5 gigawatt installation. So this kind of fluctuation is a big deal. If you perhaps put some energy storage together with this, large scale storage, you can smooth out these sort of fluctuations. The left side here, of course, shows power demand over time, and then, of course, power demand made better, smoothed out with storage. You can put energy in when you have excess energy, the wind's blowing hard. You can take energy back out. As Professor Rogers commented on a couple days ago, though, the economics, or couple minutes ago, the economics of this system are critical. Okay, we're not talking about something that's super expensive. Our grid is designed to be cheap. So if you want to make an impact, you have to be cheap. In the last couple of years, ARPA-E, the new agency for rapid response, has brought us online, and we need to be cheap enough to meet about $100 per kilowatt installed, if not better than that. Now, the flow battery systems are unique in several ways because they have some very favorable attributes. They're scalable, I already told you about that. They can be very efficient. You can operate these things, and in fact our metrics within the lab that I'll tell you about in a little bit are approaching 90% efficient, or scaled to or demand a 90% efficiency of round-trip energy conversion. These can last for a long time. In fact, for the type of flow battery we'll talk about most today, the vanadium redox flow battery, we are taking out from a fuel cell the components that cause any durability issues. So these can last for tens of thousands of hours in principle, and the redox flow batteries generally are aqueous based, therefore they're relatively safe. Again, would you want to live in a city with a lithium battery the size of a Home Depot? I wouldn't, I can guarantee you that. You can take out chunks of planes. We saw a laptop fire. Wow, I should have eaten lunch. Anyways, oh, I thought it was my stomach growling. At any rate, these are inherently safer systems. That separation of power and energy is a big deal in that respect, because you can basically you have an aqueous system. If a battery that size becomes, let's say, a terrorist target, you're going to have a little bit of acid spilled on the ground. But again, the energetic components are separated from each other. Okay. So, sorry, go back for just a second. Remember, in our flow battery, the electrolyte, so-called, on each side of the cell flows through with redox active components that are converted. Now, you can use a lot of different types of chemistry in a flow battery. I'm going to talk extensively about the all-vanadium one, so I'll reserve that. You can use iron-chromium couples, iron-cerium, zinc-bromine, hydrogen-bromine, et cetera, et cetera. There's new players, especially using air electrodes. And some old players that are being recycled that use air electrodes. These have several characteristics. First, you use simple inorganic redox couples. One of the reasons you do that is because the electrochemistry is favorable for those things. The second is things like iron are moderately cheap. They also usually use aqueous electrolytes. I often pick on ionic liquids at this point, even though we're doing some ionic liquid batteries ourselves. Ionic liquids or non-aqueous electrolytes, think about the size of that tank. When you think about it, cost-wise, it's going to be difficult. So in fact, taking advantage of the high energy densities that you may be able to get by going to high voltages with a non-aqueous electrolyte of any sort may be something that is more of a specialty situation as opposed to the commodity situation on the grid. Generally, we want the maximum voltage separation because this gives us high energy density. Again, in water, vanadium, for example, pushes the limits of that. You can do better in non-aqueous solvents. There's no question about it. But as I mentioned, you give up a lot on cost. People play tricks with complexation to get separation of redox couples and different voltage, and then cost is something that we never let go of. So here is a little cartoon of how a vanadium redox battery works. We're going to talk for the rest of the time about vanadium redox batteries. The system has two electrodes surrounding typically a ion exchange membrane or polymer electrolyte. And these are current collectors and flow fields for bringing in the vanadium solutions. The positive electrode has the high oxidation state vanadium species, vanadium 5 when you're fully charged. When you're fully charged, you have vanadium 2 on the other side. It's very colorful chemistry. As a matter of fact, these vanadium species have rather distinct colors. And so during discharge, vanadium 5 and 2 come into the electrodes. Vanadium 4 and 3 come back out. And as the battery runs, the colors change. You can see that there. And basically, that's a clear indicator of your discharge. You can in fact look to a first approximation at state of charge of the battery just by looking at the visible spectrum, the color of the solution. Okay, these vanadium flow battery systems utilize ion exchange membranes, and in fact, to improve the performance, we're going to talk about, every fuel cell guy who looks at these says, hey, this is what we can do. We can actually redesign the cell. In fact, the cell design being used in those filter presses we looked at was actually sort of flawed fundamentally. It led to very high resistance in the cell. We can actually modify the electrodes. In the vanadium case, again, it's that simple metal ion redox couple. We use primarily carbon electrodes, but they're porous. We'll show you a picture momentarily of that. And then finally, we want to work on the membrane. The battery I showed at the 1 megawatt level at the very beginning used 10,000 square meters of Nafion. DuPont was very happy, but at something like $1,000 a square meter, maybe $800 a square meter as a material, that's really going to make it hard to get down to that $100 per kilowatt situation. And so we really want to look at improved materials. We also need to truly investigate methods that will allow us to analyze and compare these materials and really develop, this is the mantra for my lab, as any of the students involved will tell you, what goes where, how fast and when to basically not only aid future modeling, but to understand what's happening in the cell. So, without further ado, we'll jump into actual data. Again, this is the cell structure, a single cell where we have inlet flow on each side. Basically, the material passes by the electrode. It's a flow-by configuration. And basically must be taken then into the structure. So we have a porous carbon structure as our actual operating electrode and then a membrane. This architecture takes us, as we'll show you shortly, from about 100 milliwatt per square centimeter typical peak power to about 1,300 milliwatt per square centimeter. So we were actually increasing by a factor of about 10 to 15 the performance over the last couple of years. Okay. We also, just to set up future slides, use extensively, borrow from fuel cells. Basically, we use polarization curves that aren't the norm for battery work, but this is a steady state flow system, so we can get away with it. Polarization curves are a very useful diagnostic because we can start to separate where the losses are in our cell and then focus on those components. So at the high end of voltage or low current densities, we typically see activation losses. That is, the intrinsic electrochemical kinetics in the electrodes starts to, or bothers us, or is the source of voltage loss in the cell. In the middle region, we have primarily ohmic dominated losses. As you might expect, the current voltage curve or voltage current curve is linear in this region approximately. By the way, these can come either from the electrolyte membrane or from the solution that is in these systems. And then finally, we have mass transport losses where we fail to be able to deliver reagents to the electrodes fast enough. We try to separate these losses, again, to pick out which electrode, which piece of the membrane, et cetera, are causing us problems. One tool we use in doing this is to use impedance. This is Josh Sun. He's a postdoc at Oak Ridge, actually. He's my group at Oak Ridge, if you will. We have flow battery work going on, by the way, both at UT and at Oak Ridge, I should mention. Basically, this is very, very clean on a device working at amps per square centimeter, potentially, type of impedance. And from this, we can start to deduce, as you can see over here, basically what's going on in the catalytically active parts, the ohmic part near the or near or within the electrode, et cetera, et cetera. Mass transport loss is called residual in this particular case. So we can actually pinpoint one piece versus another as to causing the problems in the cell using these electrochemical measurements. So our first pass at developing diagnostics were to combine the polarization and the impedance results. This gives you an idea of some results circa about a year ago. These are literature results when we started over here. This is what we were able to produce in this polarization curve, making changes in the cell structure, the electrode, and the membrane all together initially. So we went from, let's say, a maximum current density of a few hundred milliamps per square centimeter up to 1.75 amps per square centimeter. This is where we are today. Come on. Eek. I see what happened. Sorry, I didn't mention this, or I got one out of order here. We actually have done quite a bit of work to optimize the electrodes in this situation. A key thing is to make sure that we are wicking or getting from that flow-by system liquid throughout the electrode. You can see here that in fact we can variably affect the ability to transport water into this porous carbon structure, which is our electrode, by heat treating under various atmospheres, either oxygen or nitrogen. We also, in fact, this dramatically affects how much kinetics we have. The pure surface area that we access inside here is so much higher right now than when we started, that we actually need no special catalysis, et cetera, et cetera. Okay, moving on. Oh boy, did I missed one entirely? Well, maybe not. So we improved our electrodes. These are just materials that are commercial, provided by SGL and some other folks, Ballard, Carbons, Cabot, et cetera, that were tried. This is at high state of charge for the battery-oriented people, if any, in the audience. That is, we work near fully charged battery. This is with a 50% charged battery. We have a little extra mass transport loss. But the key thing is, again, a very large increase in peak power density just by dropping in a different piece of carbon. So we're starting to learn the factors now that really lead to better electrodes. Up in that kinetic regime, this is really a big change, because in fact, if we want to operate at 90%, 1.4 volts might be a good place to work. We have 4 to 5 times the increase in power in the current density there. That means we need 4 to 5 times less material for a given demand of power from our system. And so this is where we are today. Basically, we're now up to over 1,300 milliamps per square centimeter. I think our most recent results are a little over 1,400, as a matter of fact. This indicates that there's very little loss up in the kinetic regime. We access extensively the electrode surface area, and so we've reached a certain limit, which is really the limit of the IR loss within the device. That is the loss due to the polymer electrolyte membrane and loss within the electrode. We're able to extrapolate that actually and consider what's going on with some non-aqueous systems, and I don't have time to include those results today, but they're very revealing with the possibilities for prospects for non-aqueous batteries. Keep your eyes open soon. But key thing again, we have now a factor of 15 to 20 increase in the power density, a factor actually achieved here of about 8 in the current density at high efficiency points. And so we have dramatically improved the performance. Again, Josh's picture. We also are looking extensively at fundamental characteristics. This is just what we would look at as a Butler-Volmer plot. Doug Aaron, postdoc in our lab, who actually did his PhD through Georgia Tech, did these measurements. We started to do something that every electrochemist wants to do, but apparently the flow battery community hadn't done, which is put a reference electrode in there, and we actually got quite a surprise, namely that the non-oxo containing vanadium ion was more difficult in terms of electrochemical kinetics. Reviewers didn't like the fact where we put our reference electrode, so we started to look at symmetric cells. This gives us a clear indication, at any rate, of what the intrinsic reactivity of those carbon electrodes are. Not a piece of glassy carbon in a rotating disc in a cell, but in the actual device. Because in fact, we work with very high current potentiostats and so on, up to 80 amps or so. We can actually get kinetics directly out of the cell. The other area we've explored extensively is membranes. Now the membrane actually has a lot of features that are really important to us. We know a lot of different membranes that are available from our PEM fuel cell work. However, we're really starting over to understand durability in the presence of these highly oxidizing solutions and so on and so forth. And we have multiple chemistries to take into account. Material, water and vanadium, let's say, crosses over through the membrane, and so we have to understand the implications of that and how to control it. And finally, the multiple components that are present for different redox states and acid and water in a vanadium battery solution lead to extremely complex transport. The flow battery literature simply ignores this. It's a very simplistic approach that they've taken to looking at mass transport, which really determines how fast, for example, capacity will fade in the battery. So we actually almost are starting over and inventing methodologies that I'll talk about in a second. The just plain different is that you can conceivably use porous separators depending on the chemistry, and that's a little different. So again, water pumping during operation is a big deal. Those are big tanks, a lot of water. If you started to move a lot of water back and forth, the balance in the battery changes, et cetera, et cetera. And again, vanadium crossover is essentially an efficiency loss within the battery. And so we have to understand what properties of these polymer electrolytes basically control this, and then also understand the driving forces for transport. Zhizhong Tong and my group is doing extensive studies of to figure out what goes into the membrane in conjunction with these battery components, and then what the implications are. So in fact, uptake of the acid from the solution has a major effect in dehydrating the membrane. This leads to a major drop in conductivity in the membrane that's going to go in the cell. That's not good. Also, vanadium uptake leads to a major drop in conductivity, and so we need to control the partitioning of vanadium into these membranes. So we start to understand a lot of that. As I mentioned, there's a very complex transport phenomenon, or set of phenomenon, and the fluxes involved in transport of these species are all coupled. So we have actually tried to simplify this with one vanadium species at a time in the transport thing. So how hard could that be, right? You have one vanadium species on the side of a membrane crossing over, it's almost Fickian diffusion, except if you demand constant ionic strength, that is the same total sulfate, if you will, on the two sides of the membrane to cut down on water flux at the same time, you will end up having a gradient in protons and vanadium at the same time. Whereas if you basically decide to go with constant acid, so you don't have the gradient in protons, you'll have a water gradient. So you already have some coupling between fluxes in the simplest case. We're using vanadium EPR to monitor mass transport. Vanadium-4 happens to be EPR active. This is led by Jamie Lawton, and in the audience, Amanda Jones has done extensive work with Jamie doing these measurements. Jamie is the person who likes to make these little cartoons with vanadiums flying all over the place. So in fact, this is a schematic of the cell. We have a membrane between two flow channels, sets of flow channels, and we simply monitor how much vanadium arrives across the membrane after we start to flow using the world's most expensive detector, an EPR cavity. And what we find, okay, enough, is that the flux seems to be inversely related to the VO2 plus concentration. So that simple case of just putting vanadium on one side and watching it go across is weird, because in fact, the higher the concentration, the lower the apparent flux. I don't know about you, but where I come from, the bigger the concentration gradient, the bigger the flux we expected. And so that manifests itself as a major decrease in the diffusion coefficient and so on. So there's good news in this, and that is that we may actually be able to control this membrane crossover problem, that is the crossover of vanadium from one side of a cell to the other, just by controlling the acid content in the cell. Oops, I'm going backwards, sorry. So we know that vanadium unfortunately partitions easily in the membrane, drops the conductivity, but we may be able to control this, and we're really just getting started. We're working with several of our UT colleagues, for example, to understand, Stephen Pattison being prominent among them, what's the state of vanadium in the membrane and what are the properties of the pore fluid, and with Brian Edwards at UT, the effects of structure and morphology on our ability to control uptake of vanadium into the membrane. And that's just one chemistry for you. You can imagine we have to redo, basically a lot of that for every single chemistry. We've received funding from DOE Office of Electricity, the GSEP program, the NSF 10 score program, our state EPSCOR program, and our UT Governor's Chair Fund for this work. I should mention that Professor Matt Mensch in our mechanical engineering department is my close colleague. We've basically certainly merged as much as possible the flow battery parts of our group. This is his group. This is the next picture is our group as of last year. We've added a few. We've deleted one there, but basically about a third of this population is doing things in the redox flow batteries, and by the way, an increasing proportion are starting to work on, dare I say, biomass. I realize that you're not very familiar with biomass in this arena, but basically I thought I'd mention it. At any rate, with that, questions?
Any questions?
Hi, Dr. Z. Thank you so much for the presentation. I had two quick questions for you. The first you probably get all the time, and that is, how does vanadium stack up? And then the second is on the solubility of vanadium in an aqueous solution. So how does that factor into large-scale application?
Sure. I'm not sure what you mean by how does vanadium stack up.
Oh, as far as cost, I'm sorry.
Okay,
Yeah.
Yep. So one person I did not mention is my colleague, Professor Pete Counts at UT, and he's done mostly, his group, we've collaborated a bit to do cost studies. We find that vanadium, first of all, vanadium's pretty expensive. It's about 1/3 of the cost of the flow battery. By the way, 1/3 is also roughly, these are round numbers, 1/3 is also membrane costs, and everything else costs 1/3. So in fact, you're correct. For the all vanadium battery, you are really, or your implication is correct, you're locked into the vanadium pricing. Part of the answer to that may be in which grade of vanadium you use, and we're just in the infancy of trying to understand how purity of vanadium impacts its performance in the battery. And then the second question was something about scale up, or? Oh yeah, the concentration. Vanadium so first of all, in an aqueous system, of course, or in a flow battery, the concentration of the active species in the solution is a major factor, if not the major factor, in its energy density. And so, indeed, you have to try to make it as concentrated as possible. We are looking at sort of a couple molar solutions in acid in a sort of routine application. Our collaborators at Pacific Northwest National Lab have developed electrolyte formulations that boost that a bit. Vanadium is kind of touchy. We actually picked it not because we believe that this is the technology, because we were naive when we started, well, and admittedly so, but we actually felt that it would give us the most rich array of difficult problems to work on. And so, you know, all these different membrane things, it gives us sort of fodder for starting to do science as well as develop things. But people are looking heavily at commercializing vanadium batteries nonetheless. Energy density is not the glamour feature of redox flow batteries, and it probably never will be, although the ionic liquid-based battery that I have started with has actually about double the energy density of a lithium battery at the low end. But in the meantime, for vanadium, it's a fraction of a lithium battery. The advantages are in safety, ultimately, and the ability to put it on the grid without getting, you know, sort of the villagers in a torchlight parade coming to your house.
Thank you, Tom.
Thank you very much.
Well, let's thank all our speakers for this session.